Well, I'd like to thank the organizers for inviting myself to give this talk. And if you actually happen to have some unwelcome guests in your house, during the morning they've done some changes to the title. So these are the people responsible for the title. For this, what you see there. Today I wanted we're going to cover some of the things that Thomas already discussed briefly for a few minutes in his overview of the field. And the idea is to talk a little bit about spin-electronics within ferromagnetism and antiferromagnetism systems, and particularly focus on spin-over torques. So the tutorial today is going to follow a few things. We probably may not get to this point, that is just a highlight of the talk that Leeward will talk about later in the week. But we'll cover a little bit the ideas of the spin transfer torque, spin Hall effect, and the Hall effect, spin galvanic effect, and then how the typical spin-over torques that the anatomy have come to be, and how we have used this knowledge to create and come up with ideas for Néel spin-over torques that couple directly to the Néel order parameter and able to manipulate it, as has been demonstrated earlier this year in a beautiful science paper by the team in Nottingham and Prague, led by Thomas Jager. So, to begin with, instead of the spin transfer torque, the caricature is to start with the LG equations as we all know them. So you have the magnetization dynamics. The MDT is governed by an effective field, which you process about, and a damping term, a Wilbur damping term, which allows you to relax. Besides that, in a tri-layer system, as it was pointed out in 1996 by Berger and Sosensky, you can have a transfer of angular momentum from one ferromagnet to the other one via a spacer, where effectively the electrons are polarized in one ferromagnet, go through an intermediate layer, and impinge into another ferromagnet, and that ferromagnet is absorbing the angular momentum. Besides this caricature, I wanted to say a few words of how it actually happens in the anatomy, because it is important in the context of once you put a spin-over coupling. None of these in here, in the previous picture here, really requires a spin-over coupling for this to occur. And this one's shown in the analysis once you start thinking of the SD exchange interaction between the itinerants and local carriers. This interaction, of course, conserves angular momentum if you ignore spin-over coupling, and nothing would happen in terms of the total angular momentum. But the key idea, so just so that the fact that these react oppositely, but the key idea that the timescales are very different in the relaxations of the electron, the carriers, and the magnetization itself, very different as order of magnitude. And therefore, you can think of this non-equilibrium polarization that you're generating by absorbing the angular momentum from the carriers, or by other means of creating this spin accumulation, as creating a torque directly on the magnetization. So the torque itself, due to the carriers, if you have carriers that are interacting with the SD interaction with the local moments, is going to give you a torque. Now this torque, only the component perpendicular to the magnetization is going to create a torque. And that one you can decompose in two components. It's only two directions in this sphere that you have. Is M cross M and the other opposite direction. And these two components have different character, just like the LNG equation has two characters to them. One that is energy conserving, one that is not. So the first is the non-energy conserving, the one that has two products of the magnetization, M cross little m, and the other one which acts more like a field component, where M itself does not depend on M and creates like a field. Now it has a little bit of this tutorial is also to share a little bit of the jargon that is used for this type of torques, because sometimes you're going to hear different names for the same thing. Just like the song that says you call it perpendicular equilibrium pattern. It is the same thing. So the Sosensky torque, sometimes called the anti-damping torque, the spin transfer torque, the in-plane torque sometimes, depending on the geometry of the experiment, and the field-like torque, the effective field-like torque, can also be called perpendicular torque, out-of-plane torque, effective field. It's just simply defined by the geometry or its character in terms of energy. Okay? Now, when it happens in the transfer from, if you have a polarization, an incident spin current polarized impinging on a ferromagnet being absorbed, the process of transfer is really happening close to the interface. And it's really occurring in schemes that it was distilled very well by Mark Stiles. It was not done by Mark Stiles, but it really described well by Mark Stiles. And when he shows that once you actually have a reflection, there's actually a shift or a random shift depending on the momentum up on reflection of the spin. And once you average over the entire equivalent zone of the Fermi surface, it averages to zero, so there's hardly no reflection coming back. And the absorption itself, once it gets transferred, because the electrons, the majority and the minority carriers have different energies and different different kFs, they actually dephase once you average out because these are non-coherent quasi-particles flowing into the system. And that also gives you a decay length that gets absorbed directly into the ferromagnet. This gives you the idea of this circuit theory that was developed by Bratas and Bauer and others. This is the origin of this spin mixing conductance, where you essentially are solving a problem of a scattering theory, where you have a polarized electron that gets scattered back, and you define this mixing conductance in terms of 1 minus the reflectance in different channels times the reflectance in the other channel. And without the presence of a spin-orbit coupling, this is calculated, by the way, and in this case it's well defined, and then it defines the ratio between the damping and the field-like component. So the real part describes the successive torque type part, and the imaginary part, the field-like component. And those things you can calculate directly by an issue or another means. And then here you have a little more, the torque itself, as I mentioned, has those two ratios. And the actual mixing conductance is defined also in terms of the direction of where this spin accumulation points of the electrons. Now, once you go into spin-orbit coupling at the interfaces, as is occurring in many of the experiments, I want to highlight that the spin mixing conductance is a bit of a misnomer now. It can be defined then by different ratios, but many other things are going to happen. This simple decoupling that occurred once you don't have a spin orbit, assuming that you don't have any spin loss at the interface, is not going to occur. And the anatomy itself is going to become more complex. Some things are going to dephase and some things are not anymore. And this is the work that is recently done by also Mark Stiles and Vivek Amin in a recent of 2 papers, very longish papers, but quite important to read, where you really show that now at the interface, besides this transfer angular momentum, you also have a generation of spin currents. So the circuit theory that was created is going to have also some spin generators into these interfaces, and things are going to be more complex in terms of the analysis of this spin transfer torque and the spin electronics, where spin orbit coupling comes into play. So that's one part. And you also, of course, the spin transfer torque, the physics of it, has been utilized and is being utilized now in membrane technology. It scales quite well. It has lower power than the typical ones done with taggles with the magnetic field. And it has a simpler fabrication, but it has one problem, that the actual reading voltage and the breakdown voltage, because you're actually running a lot of current in order to actually be able to transfer and overcome the damping of one of the ferromagnets that you want to switch, and that one sometimes overlaps and burns. So essentially your devices tend to melt rather than break down in terms of crashing of the devices of hard disks. And this is why in the news, the last few years, there's been a lot of interest in this type of geometry, in type of switching the ferromagnets, not for the reading point, you don't need a lot of voltage, but if you actually now write your current, you write your bit by running a current through the most conductive part of your element, then you don't have so much heating. So you would not have the problem of meltdown anymore. But the question is, can you actually do it? Can you do the efficiency? It's not a question anymore, as you know. This is something that has been done, and this is where the story of the spin Hall effect and the inverse spin galvanic effect comes into play in this physics of MRAM technology in creating a much more efficient way of doing switching, or if not efficient, definitely faster, but less heating involved. So this is where we go next, which is introducing the idea of the spin Hall effect. I don't think I need to introduce it, but that's for completeness. This is the physics. Of course, it was by the analogy with the anomalous effect. It was stated by Jairo Sinova in 1971. And it simply means that in a paramagnet, you can have a deflection, spin-dependent deflection due to the spin-orbit coupling, either due to impurities or to the band structure itself, so the intrinsic component or the extrinsic spin Hall effect, and generate a spin current. So it's essentially a spin current generator perpendicular to a current that you flow through your paramagnet. There were two, there's a review now that we've written out. There's also a very nice review, more focused on devices by Hoffman. But you have here the intrinsic and the extrinsic in two experiments that appeared at the same time in 2004. Once in PIDO, the strongly spin-orbit coupled systems, and once in weakly spin-orbit coupled systems by Rashiba. Now, I want to explain a little bit of the intrinsic part, because the extrinsic is quite easy to understand. You have an electron, it's a spin-orbit coupled impurity, and depending on its sign, it is guided to the left or the right, depending on the spin. That's simple. To understand the intrinsic one, which actually has an impact on the spin-orbit torques generated by the inverse spin galvanic effect, which has a lot of mirrors and similarities, you need to think a little bit more of what it actually means. Effectively, what it means is that if you have, here I'm going to use an example of the Rashiba spin-orbit coupled system, two-dimensional one, where you have electrons here in the Fermi surface just pointing along this direction. There's, of course, another band in the opposite chirality, but just for simplicity, I just show one of the bands. And as you put an electric field, this accelerates and changes the momentum of the electrons. And as this momentum is changing, because it has an effective field proportional to its momentum that points perpendicular to that change in momentum, whereas at the beginning and equilibrium, the momentum was pointing perpendicular to K. Now, as I changed it, there's going to be an extra effective field not line up with the spin as it changes its momentum. This is going to create a precession, okay? And the precession that is going to have for these electrons down, for these electrons up, and as you can see, the electrons moving to the forward and to the right are pointing down, the ones moving forward and to the left are pointing up. So that creates effectively spin current in this direction and a charge flow in that direction. That is effective, but you see the coherence in this case. The coherence is coming through the acceleration process. You need coherence between the two bands. You need a spin-orbit coupling in the bands. This is why the intrinsic nature of it comes from. So as I mentioned, the first experiment I observed that, as Thomas was describing yesterday, was on a beautiful experiment by Wunderlich, the Bloch Wunderlich, that used a planar LED type of structure with PIDO galvanized night. And then there you observe in each of, as you run a current in each of the sides, you see opposite polarized light emitted under the recombination process. But at the same time, in this system, there is another process that generates, in this case, not a spin current, and a spin accumulation of opposite signs in the opposite sides, but also a homogeneous polarization on the plane. This is the so-called Einstein effect in two dimensions, or this inverse spin galvanic effect, and it was observed in both systems at the same time in the same device. And what it is that as you now look at this Fermi surface, once you put a current, you essentially are unpopulating this side, populating that side, and generates this charge current that effectively, if you sum things up, you see that there is an in-plane component of the polarization of the carriers. Okay? But in this case, it's not a current itself, because both the one to the left and going to the right have the same polarization contribution perpendicular to the current, and that generates this non-equilibrium polarization. Okay? And that's the inverse spin galvanic effect. Now, how is that utilized and exploited? Now, this one was, too fast. This one was then exploited and observed By coupling, this one observed, of course, in the paramagnet, there's no ferromagnetism whatsoever there. In that system, you just have a non-equilibrium polarization present once you run a current and observe the polarization coming out of the carriers. But in order, once you couple it with a magnetic system, like in gallium nitride, the first experiment that was coupled to that essentially generated effectively a torque was by the group in Purdue, initiated by Robinson, and in the paper by Chernisov. And in there, you actually can observe the tilt of the magnetization once you run a current in this big old gallium manganese arsenide, which is a ferromagnet. Of course, this ferromagnet is a beautiful ferromagnet in terms of being quite simple. If you grow the materials correctly and control the material parameters, but of course it's not going to be practical in any sort of sense because the TC is like 200, it's not going to go into any device. And it was also the interest really sparked as well once this thing was also observed in metallic systems by the Railroad group, by Mirror et al., by looking at the main monophiliation differences in the perpendicular geometry. Now, still, this one is just the observation that you can modify the magnetization by current, not totally switch it. And in 2011, 2012, I think, the two experiments that really sparked this idea of spin-orbit probes appear, particularly 2011 paper of Mirror and 11. And this is where you have a structure that you have platinum, cobalt with a perpendicular anisotropy and an oxide, and you run a current and you're able to switch it back and forth, just like that structure that I mentioned to you earlier that you would like to reach in the new MRAM type of architecture. The first possible interpretations is that the physics in here was assigned to the physics of this Rashiba system at the interface, or Rashiba spin-orbit couple at the interface, which could have a field-like component, just like I mentioned, that you have to create a non-equilibrium polarization. Now it couples through SD exchange, and it creates a torque. But this torque, primarily, it is in the sense of the field-like component, or believed to be of a field-like component, although they pointed out as well that it also has an anti-damping dissipative component in this experiment as well, but assigning to the fact that the spins have different spin ups and spin downs, and this really didn't quite match with the theory because the spin plus and spin minus, they don't have orders of magnitude difference in terms of the spin phasing, of the lifetime phasing of the quasi-particles. Now you also have a similar experiment with a different geometry where they do FMR type of experiment that I'll explain to you in a minute how that works. But in this case, you run the current, and the interpretation of the Cornell group, of Van Roth's group, was that in this case you have primarily assigned the character, which is assigned to the anti-damping component that you can see is of a Solzhenitsyn type. And they all said, well, the only physics that can give me that type of physics is by assuming that I'm generating a spin current due to the spin Hall effect flowing in here and being absorbed by the ferromagnet, and that gives me essentially the torque itself, and it would be very natural, just like the Solzhenitsyn torque primarily is of anti-damping nature. It has a small component, a field-like component. That's what we will observe. So just to summarize, you have these two types of possibilities of torque. One by generating a spin current that can flow into the ferromagnet, and another contribution due to the spin accumulation generated by a flow of current at the interface that generates this non-equilibrium polarization that can couple to the magnetization flow at the interface. But the problem is that both of them, in reality, can generate both. This one will generate primarily anti-damping one. This one was believed at that time to be primarily field-like, but as I'm going to show you, you can really generate both of them. So from the point of view of symmetry itself, you cannot distinguish them. And this is where a little bit of the mess came, and now I think we are now beginning to clear it out or understand it. But there's a lot of names. The problem is once you name something due to the origin of it, then if it stacks, it creates confusion. So this type of torque in the Bilayer system, sometimes it was called a spin Hall torque. By saying that, you're saying that the spin Hall is the only one responsible for it. But, you know, the only assigning that into the symmetry of the torque. And then you don't, you know, and then you're making a sweep assumption that the Rashiba contribution, the Edelstein contribution, the induced galvanic contribution is 0, which is not the case. The same thing as well for the Rashiba torque, because in that case, mostly you say it's a field-like torque. So in that case, I would actually promote that spin Hall torque and Rashiba torque are related that way, and just call it a field-like or anti-damping-like. That's probably, because in that sense, you're only talking about the geometry of the torque that you actually measure. This is probably a better bet in terms of assigning some physics of it. Why you actually can have two types, and I'm going to focus now on what I will call the generation of the spin Hall by spin transfer torque. Many people are calling that the spin orbit torque as well, and rightly so, because the spin current generated is due to the spin orbit coupling. But myself, when I think of spin orbit torques, I think that it was just the ones linked to the non-equilibrium polarization generated by the current and by the carriers that couple to the magnetization. So the Edelstein effect or the induced galvanic effect. And in here you have a field-like component, just like I mentioned earlier. The field-like component will be similar to the extrinsic SQ scattering, and also the field-like spin orbit torque, just like I defined it. And in this case, what I mean field-like is that this non-equilibrium polarization is very independent, or quite independent, of the magnetization direction relative to this current. So essentially, that's why it's field-like, because it's independent of the magnetization and it will process about it. But there is another contribution to the carriers that arises of this non-equilibrium polarization that arises due to the physics very similar to the intrinsic spin Hall effect, which is the fact that you also have that the carriers are changing its nature, are flipping, are tumbling around during the acceleration process. Okay, it's not only the distribution of the Fermi surface that happens when you have current, but also the nature of the carriers multiplied by the equilibrium distribution function that can give a contribution. This is the reactive part of the response function, which can also generate, just similarly as it generates an intrinsic spin current, it can generate an intrinsic spin accumulation in the carriers. Now this one, I'm in my own chair, so I can skip it by the time. But you can see, you know, this is just essentially a formula. This is for you. In this case, it means that okay, once we have band crosses nearby, you're going to have a near the Fermi surface. You're going to have a large contribution. But looking at the formula, it doesn't give you the physics too easily of why it is that is giving you spin orbit torque and why is it of this anti-damping contribution. You can see it better by the pictures that I just showed you. This is why actually I insisted on showing you this picture of the intrinsic spin Hall effect, because it's now you actually create a system where you have a magnetization that is strongly exchange coupled. So you're in a large exchange limit that effectively lines up or anti-lines up in this case, the equilibrium spins with the magnetization. But remember that you still have a Rashiba spin orbit coupling underneath. Okay, it's not very strong, but it's the only one that has an angular dependence. So if you now start moving, so you start moving it as well, as it accelerates, the only change in effective magnetic field is going to be again due to the Rashiba interaction underneath in the carriers, which is they still have, and perpendicular to its motion, to its momentum in the x direction, the changing momentum in the x direction here. And in this case, they're not going to create a spin current in this limit. They're going to create a spin accumulation perpendicular to the plane, not in the plane. Okay? Keep in mind that it's in addition to the one in the plane. So you have a perpendicular and in-plane polarization just from the extrinsic contribution, I feel like. But now you have one that is out of the plane, and more important than anything, it depends on the direction of the magnetization relative to the current. Whereas the opposite didn't. The opposite, the only thing that defined the direction of the in-plane component is the direction of the current. Very little has to do with the magnetization itself. And you can see this because in this case I of course show you the maximum component which is pointing down, but if I actually put the magnetization perpendicular to the electric field, perpendicular to the current, you end up with effectively 0. Because as you accelerate, your spins are already lined up with effective magnetic field that you're generating more and more. So effectively it's zero. And you can see that the angular dependencies, if you work it out, is essentially of this non-equilibrium polarization pointing out of the plane is cosine of the angle between the magnetization and the current. Okay. This is for the Rashiba component, of course, but for the Rashiba itself is actually isotropic in terms of the x direction, and so there's not really any crystalline orientation that you can identify. If you have a Dresselhaus type of spin-orbit coupling and you run a current in the different directions, you can actually figure out the actual angular dependence just by looking at the phases between one and the other. So in this case, if you run it in the x direction compared to this one, it is shifted by minus 90 degrees, so you're going to have a sine angle dependence. If you go in this direction, it's going to be minus sine, cosine, which is the same as that one. This direction is going to be minus sine, etc. You can see it in this table. What I'm after now is to show you that whereas in the bilayer system, you mix the system with the spin Hall effect and the Rashiba at the same time, you can actually take one out in an experiment where you can have this controlled spin-orbit coupling and just a single layer. So there's no spin Hall effect to be talked about, but only the spin-orbit torque. Or in this case, we're aiming it to do it with gallium manganese arsenide because different strains control the different contributions, linear in momentum in this case. How you actually do it in terms of the techniques is, just as Brian mentioned yesterday, is this FMR technique where you're exploiting, you're essentially exciting the system in FMR with a small magnetization, a magnetic field that excites the magnetic component. But in this case, the small, you're actually reversing that. You're inverting that by saying, I'm going to drive a microwave current through my sample, and then I'm going to generate a resonance. And by analyzing this resonance, I'm going to extract what this internal field and the symmetry of it is nothing more. This is this FMR technique. And there you actually have, just looking decomposing into symmetric and antisymmetric component gives you the two components, the anti-damping anticipative component of the torques and the angular dependence that we're looking at. There's the natural dependence of this signal just from the energy equation. So the symmetric component will have a sine of 2 theta and cosine of theta in this case of this asymmetric one. But the key thing now that you can get rid of that by dividing by sine theta and look at whether this h of z and the other components have an angular dependence. The ones in the plane, as I'm not going to talk about those have very little angular dependence, essentially they are field-like. But the symmetric component is the one that is anti-damping like, and just as we showed in an experiment a couple of years ago, this one has, in a sense, a very strong anti-damping component. So the spin-orbit torque arising from the Rashiba, if you want to call it before, or the inverse field galvanic effect coupled to the magnetization, it gives you both field-like and anti-damping depending on the strength of the spin-orbit coupling, depending on several factors. This is what I think the field is going after, because this was for gallium manganese arsenide. You can also now look at an actual metal and look at, in this case, half Oysters with similar structure, nickel, manganese, and timonite, and experiments that showed that you can actually have also feel like at room temperature. It was dominated in this case by the feel like component. That one is now, in this case, it's more feel-like component, but shown at room temperature by a recent paper by Sarah. Now, there's other techniques to measure the torques, okay, but still at the end of the day, the torques, what they measure is the symmetry of the torques. There's the magnetization switching, there's the AC voltage technique, there's the DC component to the SMR that I mentioned to you, as well as mode and domain ball motion. There's a bit of a list, and I bore extensively, by the way, by Pietro Gambardella talk of last year in a couple of, in a very beautiful tutorial that he had, so some of the slides are thanks to him. So if he sees this, thank you, Pietro. Now, let's move on to the antiferromagnetic part, okay, the last 20 minutes or so. Okay, so up to here, Now we've established that we have spin-over torques, both of the spin Hall effect generating a spin current that is absorbed and gets the torque, as well as spin-over torques due to the carriers themselves, creating a non-equilibrium polarization and torque in the magnetization. The question is, can you actually do something similar in antiferromagnets? The answer, of course, is yes, just as Thomas mentioned yesterday. And this is one thing that we need to understand, is that, this inverse galvanic effect, once you put an antiferromagnet, there was a beautiful realization that in this case, by Jakub Seletny here, we also have a talk later in the workshop, where you have to realize that the spin-over coupling is a local effect. It really comes from the co-electrons of the atoms. Okay? So locally itself, you're going to generate a lot of this spin-over coupling due to the atoms themselves locally. And you can actually have a system that is actually centrosymmetric, which in this case you will imagine that it has no spin-over coupling effects whatsoever. That's what we've been taught and believed for a long time. But realize that this system is actually coupled by two broken inversion partners, broken inversion symmetry partners. Here you can see the example is in manganese to gold, where you actually have, if you look at this sublattice and this other sublattice, the gold atom here and the gold atom here is in different spots, okay, creating essentially two broken inversion symmetry pairs. Now, before, of course, average over the entire unit cell, the Hall effect would be 0. But if you run a current through this and you try to generate a spin-over coupling to that, a non-equilibrium polarization, you would effectively maybe guess, this is what Thomas guessed, that we will calculate later, that you actually, the same Rashiba physics that I was describing, particularly the field-like Rashiba physics that I was telling you about, is there, but in opposite signs, in opposite sublattices. So in this case, by running a current, the sublattice of the red and the sublattice of the blue component will have opposite signs, which is the case. And so in this case, as I will show you. We thought initially that this was actually due to the physics of the broken inversion symmetry being broken by the order state itself, but in reality it's not, because this is a field-like component in a way of non-equilibrium polarization. In this case, in AL type, so it's a staggered non-equilibrium polarization that is generated in a staggered non-equilibrium spin accumulation, and it's independent of if you're in the paramagnetic state or in the order state of the antiferromagnet, is still there. But of course, any experiment will tell you that, look, anything that varies in the order of the unit cell, I cannot couple to my average over many unit cells, except that nature gives you something to couple to in that length scale, which is the Néel order parameter. So it does vary in that length scale of sublattice to sublattice. We calculated the effective field that you can generate in there, and this is, of course, this Néel spin-over torque. And you can see that it's field-like because the angular dependence, this is the angular dependence in the XY axis, and this is the angular dependence between the Z x-axis. And it varies a little bit, but not a lot, and it's opposite for equal opposite sublattice. Sublattice A and B have the opposite sign. And this is the non-equilibrium polarization generated particularly close to these electrons, these atoms. Okay. Now, effectively, what this is doing is essentially generating. It's as if you can think of it as if you have some coils wrapped around each sublattice in opposite direction. Okay. It was generated by Frank Freiman. It's this crazy figure. He actually generated all, not by actually clicking the things with it, but actually by writing the script actually to generate that. It's pretty amazing. But what you do essentially, you can think of it as you run the current, you effectively are creating you know, here, if you wrap your coils, you're creating effective magnetic field with opposite signs in opposite sides, and there this rear head. Okay. Notice that the chirality of the solenoid, atomistic solenoid coils are there. Okay. Just so you have an idea of course, it's not coils themselves. That's the idea. If you actually put in now that you have both, you have now a marriage, a different type of table that you can put the type of spinor retorts that we have. Ones where the two are the same in the two sublattices, okay, or anti-damping in the two sublattices, and one where the two sublattices have opposite signs, and this is the one that I just told you about. But there's also going to be another component similar to the one that I told you earlier. That is, this field, this effective field-like nail spinor retort, is quite exploitable, not only for the reorientation of the domains, as you saw, and I will show you the experiment that was there earlier down in the year, but also to move the domain walls in a staggering, very, it's not next talk, sorry, that was I borrowed from another slide. That was from previous conference, where you actually can generate very clean, very fast moving domain walls and in a very efficient way. That doesn't depend too much on the nature, particularly because it's a ponder multiforce, I learned that word from Helen, because it doesn't depend on the nature of the domain wall, where it's nail or block. Is quite useful in terms of moving the domain walls, and the one most of the cells will move very, very fast. The very, very fast has nothing to do with the fact that it's a nail spinor retort, is because of the natural limit of the speed and spin waves in a ferrom and an antiferromagnet. That is still superior, I'm sorry, than 2006. But the point that I also wanted to make is that you also have this anti-damping one of type that's not been observed yet. And this one would be if you actually have now a system where you have an antiferromagnetic with a homogeneous spinor coupling field that is seen by both sublattices the same. In this case, you would not have essentially the actual opposite components would cancel, and you would only end up left with a contribution to this effective field that depends now strongly on the angular dependence, similar to the one that I showed you about the anti-damping spinor retort in ferromagnets that we observe in gallium manganese arsenide and nickel manganese antimonide. Now, it is one of the important things to realize in this case that it is much stronger, this effect will be much stronger than in ferromagnets, because in ferromagnets you probably don't remember the equation, but you have 1 over the difference of the bands that are coupled square in the denominator that reduces that effectiveness quite strongly. So in the ferromagnet you have the gap itself, the exchange gap all the time, whereas in an antiferromagnet, here you have this exchange gap that is very natural, so all the bands are separated. In an antiferromagnet we have mostly here, the split is due to the spin-orbit coupling only, and you end up with, instead of, if you just create the same model of ferromagnet with antiferromagnet, the actual torque, the actual effective magnetic field is 2 orders of magnitude larger from the Pearson dynamics. So in that sense, it could be made stronger. Whether it's useful or not, we don't know, because just as Helen was pointing out, the dynamics, because it's the Newton dynamics that is following, rather than the more linear, the one with Maxwell's dynamics of the energy equation, it is not clear that this would be useful for switching anything directly, but certainly from torquing and manipulating the magnetization, it definitely would have an impact. The experiment itself was actually beautiful because it was predicted now 2 years ago, or maybe a year and a half ago, and now observed not too long after that in copper manganese arsenide that has the same structure as manganese to gold, and in gorgeous experiments in science where they show the flipping, they run the current, and they show the switching, very controlled switching. And not only that, as Xavier Martin will show you later in the week, you can actually go to an actual device where you have 1 year later a SUV stick that you can actually plug in the computer, and you see the switches back and forth. Essentially the first antiferromagnetic all-electric memory that you can put in a magnetic field and nothing happens. You will fry up your laptop before it flies out back to the device. So it's totally radiation insensitive and things like that. Now, in the last 10 minutes of the talk, this is what Thomas mentioned yesterday. They have ultra-fast switching. Now it's getting better and better. They have new devices that we showed last week. But the switch is very, very fast and very precisely. So this technology maybe has a possibility, quite a strong possibility, you can see. In the last thing of part of spintronics, spintronics in the ferromagnets, I just want to highlight, because you're going to see the talk by Libor later on, the work, the beautiful work, particularly initiated by Libor, where you're trying to think of marrying two areas that has really been developing strongly in the last decade. In the right-hand side, of course, we have the spintronics community with spin Hall effect, quantum spin Hall effect, spin retort, the other spin retort, and the topological community that started from graphene about the same time as the spin Hall effect. We went to topological isolators that are still coupled to this, but then 3D, Dirac Wassman metals, it has gotten a life of its own, of course, and whether you can actually marry the two together. This is where what Thomas mentioned yesterday, that you can think now of a serendipity in a sense, or I don't know if there's something deeper behind it, that the symmetries that allow for this Dirac physics, biophysics, that require the speech-free symmetry being there, and then two sides of lattice in this unit cell that appear effectively in graphene, are also the same physics that allow for this Neil spin orbit approach to exist. And see it. This has a very important thing by and this is, as I mentioned, a work promoted by Smyko. I never pronounced your name correctly, sorry. Where he came to us and to Thomas, I think we can control the Dirac convalescent metals by the Neil port, because in the particular case in copper manganese arsenide, you can actually have some crossings, different depending whether you have tetragonal or rhombic symmetries. In one time it's a half metal, the other one is away from the Fermi surface, gaps. But these gaps now, whether they are protected or not protected versus a spin-orbit coupling, depend on the direction of the nail spin-orbit torque, of the nail or the parameter. So if it's in one particular direction, it's protected, they're protected by what is called non-symorphic symmetries that Libor had to explain to me what they were. So essentially it's true axis rotation with a light plane. And that itself, then you're able to essentially, by running a current in a particular direction and controlling by a current the direction of the nail or the parameter, just as it was shown in the experiment, you can open or close this Dirac state. So you control topological phases via a current, via manipulating the current itself directly. So this is just a highlight of what you will hear on Thursday, I believe, on the talk. So with that, I think I have talked enough. I think I'm going to wrap it a little closer to have plenty of time for the questions and time break. So this idea of spin-electronics and antiferromagnetic spintronics, or antiferromagnetic spin-electronics, and the names become a little bit too entangled nowadays, I think it's a beautiful physics of merging many ideas, borrowing many ideas and asking the question, can it happen here? And completely counterintuitive to how we thought about it before, particularly cases where you actually can generate something that really varies in a very rapid length span. Essentially, you're effectively generating very localized, very staggered non-equilibrium polarization from carriers that are totally delocalized throughout the unit cell, but generated this actual pattern that allows you to manipulate non-equilibrium spin-orbit torques. I've mentioned this, of course, in the, there's a lot of things that I haven't highlighted in this short talk. There's many physics, like the Skirvin physics that was covered by other talks. That, of course, is embedded as well as a spin-electronics in a sense, because the most instrument interaction requires a spin-orbit coupling. So underneath all of these physics appear with that. But with that, I think I'll finish, and I'll take any comments or questions. Thank you. So we have a bit of time for questions. Hope I went slowly enough. I was so clear that there's no single question. So unclear that there's no single question. Yeah.
So, very nice introduction to the tutorial. At the beginning, you start from spin transfer torque.
Yeah.
As far as I learned, that people make nanopillars because the spin transfer torque will need a certain critical current that can exceed the current.
You have to overcome the reduction, correct?
Yes, yes. With spin orbit torque, I see in most of the experiments, people also make kind of pillars.
Oh, okay.
Is there a particular reason?
No, this actually, I can show you the cell apart, but this is actually the pillar. In this case, you meant by the group of back to the flight. Probably this one is not very good. I'm going very fast back. Okay, there you go. Okay, there. Okay, that's the one. So the answer is no in this particular case. The pillar itself, the construction is because they were using pillars, but this one is just to detect whether this has flipped or not. Okay? So in this case, it's not really, you're not really flipping this one, generating a spin current to go through that. You're actually just detecting whether this one has flipped or not with this pillar structure. The key thing of efficiency that you actually can have that is a little bit better, if you think about the spin transfer torque, an electron comes in, and it goes and gives some of its angular momentum to the other side. The maximum that you're going to have is an h bar, that's it, of the order of h bar, per electron passing to the other side. Okay? And one electron, one h bar. In this particular case, a little bit different. You have a very small effect, which is actually quite unique here. The spin Hall effect is small. This is what Alan said famously one time. It's difficult because shape is small. But that's good. In this case, the problem is that it is small, but if you actually change the geometry, in this case, it's a small current that you have driven here, but you have a large area. Okay? So that's one factor that you can gain in terms of how much spin current flow you can actually generate. And effectively, just as you saw, every time the electron doesn't, is absorbing or creating angular momentum from the lattice, it's kind of reversing a flow. Many times the spin itself loses its polarization, the non-equivalent polarization to the lattice based on spin-orbit coupling. In this case, by generating this current, you're extracting coherent angular momentum from the lattice. So every time it collides, it generates one more. So it's like, boom, I'm giving it to you, boom, I'm giving it to you again, accelerate, boom, I'm giving it to you. So you actually have more h bars per electron in this case, even though it's like in one case I have one big kick, in this one I have very small kicks, but a lot of them. You see? That's why the efficiency comes in, and that's why you don't need such a large, the current itself, you don't need such a large current. Okay. Yeah.
You explained spin-orbit torques which come from the interaction of spin with lattice. In antiferromagnets, we need very complicated exchange interactions which are anisotropic and also related with directions in lattice. How do you think can this complicated exchange interaction give rise to the same phenomena as in ferromagnets, as result from spin-orbit coupling, but with a higher strength, because exchange interactions are really much more.
I think there's two parts, because when I was talking about spin transfer torque, this SD exchange, it was helping in terms of defacing things once you actually reflect and then go forward and an average of the Fermi surface. Okay? And there you don't need a spin-orbit coupling at all. And in there, probably the defacing will be much faster than the ferromagnets, that component of the transferring of this the spin accumulation into antiferromagnet. So it is stronger in terms of this physics of defacing that Mark's data show, it would be stronger. And probably the efficiency will go down a little bit. On the other hand, the one created by the Nail spin orbit torques, here you're making an assumption that the timescales of the electrons of the carriers to equilibrate compared to any motion of the other parameter is faster. So you're creating a steady motion, this is steady field compared to the exchange to ferromagnets. So in that sense, it will create those torques irrespectively until we begin to have those timescales being similar, which for antiferromagnets, for ferromagnets it works extremely well, in fact 4 orders of magnitude, even more. For antiferromagnets you're getting terahertz, and you still have a few orders of magnitude, but I think probably in this case we'll be able to think a little bit of what that actually means. Then terms of the dynamics, the problem is that of course with antiferromagnets, the easy thing that we always thought is, oh, you just run a current, you flip back and forth very deterministically, just as you showed in the talk that we're trying to work out, is not the same. To actually flip, you have to flip to that and that. And the flipping itself, because it has effective mass, is not so easy. So how you exploit these torques to flip or manipulate controllably the antiferromagnet, this is a thing that we're finding it's not so simple. Right? If you add to it more complex isotropic and isotopies, maybe facilitates it, maybe not. That's something that we need to explore. The famous table that we're trying to refine. Any more comments? You have a comment? Yeah, you did make a comment. Yeah.
Just a little comment, because I think...
But let's just period.
In the spin transfer torque, Helen, I think it's a little bit to your question. In the spin transfer torque, what we talk about is you have the carriers that precess around the magnetization, and then it's the magnetization that precesses around the spin polarization of the carriers. And that's the two time scales that Jairo was talking about, that the precession of the magnetization is much lower than the precession of the carriers. And I was wondering how it would work in antiferromagnets, where the magnetization or antiferromagnetization precession would be much faster. But I think that would apply to the spin transfer torque. But for the spin orbit torque, you have the non-equilibrium spin polarization there, even in the absence of magnetization, right?
Yep.
You take a paramagnetic phase of your antiferromagnet above the nil temperature, you run electrical current, and you will generate this non-equilibrium staggered spin polarization. It's going to be there like a field independent of the magnetization. That means independent of the dynamics. It's not an effect of precessing around the magnetization.
So
it's picking up this spin angular momentum, staggered spin angular momentum from the lattice, independent of the magnetization. So I don't think that there's going to be any problem for this particular
for that
orbit torque, for the spin transfer spin orbit torque from injecting spin polarized carriers from a ferromagnet to spin hole into an antiferromagnet, where you start to think about precessing around the sublattice magnetization, then yes, then you would have to think about this.
But Thomas, I mean, I'm sorry, I was thinking of the anti-damping one, but the anti-damping one would have the same issue. So the spin orbit torque, so the field-like component, as Thomas mentioned, is right. Since that is just constant, you should reach a steady state. Maybe it's affected by anisotropies more, because you still have some dependence, as you saw, maybe not. But the anti-damping one, which does depend on the orientation, relative orientation, those timescales will come into play, for sure. And and also it also depends on how far in terms of energy, these splittings occur, because then you capture things. So even in the spin orbital light, for one component, physics will be more complex, I think. But it's still, I believe it's still, we're several orders of magnitude away between those two timescales. So I think it's okay for quite a while. I'll be surprised otherwise. I like all the students asking questions.
Trying to ask a question that may be useful to students.
Yeah, for a theory tutorial, any experimentalist will ask like a student.
Mainly, I was wondering if you could comment on some practical matter. When we want to use these spin-orbitals, of course, the ultimate goal is to use as small electric currents as we can get away with for manipulating magnetization. So when some of the early experiments, for example, the one up there from Lucia were done, they were interpreted then in terms of the Hall angles. But now we know things are much more complicated, interfacial effects. So what is a useful quantity to report experimentally that is reasonably independent of the underlying models, but may still be useful to theorists to compare to models?
To tell you about the origin of the switching, or?
Well, how large the torques are.
Well, the torques themselves, you know them, and from what is useful for us is the magnitude of torques, which you can measure. That's how they in many resistance or relative to each other. And what is more useful for us is really the interdependence of different things. If you just have one device and you measure it, you say, well, that's a spin Hall angle, that's an effective spin Hall angle. I'm making the assumption that nothing else but the spin Hall fragments. But I could also turn it around and say, I can give you an effective Rashiba effective parameter and tell you that this is a huge Rashiba spin-orbit coupling in the interface. Either one, I could mix it. But then now if you start, one of the reasons why, for example, they attested that this was due to the Rashiba is the dependence on the actual width of this element, the cobalt, the thickness. So they were trying to parameterize by saying, look, is the physics interface, is the physics non-interface? This is where for us, in terms of modeling, need to guide you. To say, okay, grow it this way, you get a stronger torque, because at the end of the day, you care about the torque. The currents now, I think there's definitely lower now enough to be a problem. Okay, but definitely the strength of the torque is what you need. And there is going to depend on the spin-orbit coupling that you're going to generate. You're going to have, of course, some indication of the amount of current, which is linear in the current. But that's going to be determined, because of these guys, as far as I know, the conductance of these metals, they're not changing a hell of a lot. So you're not going to change it, unless you make it extremely thin, completely radically. What you're going to change a lot more is the strength of that torque. If it is due to the spin Hall effect, it is going to depend on the bulk part. But if it's due to the Rashiba, then you can maybe control also how close these bands are to each other. And they can have different strengths. Just like you did, the calculation that they were, that the unit folks were doing and you were doing. Seeing actually more agreement than you should have probably, but hey, it works. And this is where I think it's more important. Different materials, and they're beginning to actually have predicted, the things that now, for example, for the single layer where we have no spin Hall effect, and begin to look at these materials that themselves have just a spin-orbit torque, as I call it, a spin-orbit torque, and say, okay, I can predict them, I can get the numbers, and it's just that. That's, I think, where it would be useful. I don't know if I haven't answered really your question. It's more like a political debate. Just flip it around and have a good answer for that. For the antiferromagnets, the issue, we have a beautiful tool now with an L1, which is just an energetic vesicle. This way or that way, where the anti-damping ones, the ones that are useful for the ferromagnets, become useful here. That's what I really learned in the last, learned from Helen particularly. And she's just like, oh no, baby, you're thinking of this like a child. This is not as easy as you thought. It's much more complicated. Just like mathematical life is not as easy as simple as you think. Particularly the antiferromagnets. Okay. That Thomas wants to make another comment, but I can see it in his face. So let him make another comment, and then we'll go for a coffee.
Just a quick comment that in ferromagnets in the spin-orbit torque, yes, people like the damping because it's multiplied, the field is multiplied by the Gilbert damping, so you require a smaller field for switching. But not people believe that what you need to have this deterministic fast switching with the spin-orbit torque is also a little bit of field-like component, because the field-like component is helping to make it deterministic and very fast. So maybe for antiferromagnets, an anti-damping torque would not be the best torque for the switching, but maybe it would help. You would have a strong field-like turn, but with a little bit of anti-damping, maybe you can switch it faster, more efficient, more deterministic.
We need to figure that out. Okay. Now she has her beauty. Okay, I think that's enough for now. Let's have a break. I'll have a coffee break, and thank you for listening.